Okay, so today is an important chapter. It's the foundation of many things you'll learn in the future. And also, this will actually illustrate a lot of concepts. It'll sort of tell you why you'll learn differential equations and that kind of stuff. All right, so let's see what it is about. Okay, so you can attach, see, I've attached a mass to a spring, and okay. And you see this system, so I'll give you some terminology that you'll hear. Okay, so here's a system that is evolving in time. Okay, its configuration is changing with time. So this system, this is called a dynamical system. Okay? And what you want to understand a system like this. So in real life, it could be a stock price that is changing with time. You could be in the wild where you have predators and prey. So as the predator population goes up, then the prey population will go down, and then that'll lead to predator population going down, the prey population going up. And so you see that the population will change. That's a dynamical system. All right, so this is one of the simplest dynamical system that you will study. Okay? And you can see that this is an oscillatory system. Okay? So you can see that this motion is repeating itself. Okay? And as long as there is no damping, what does damping mean? I'm sorry? Friction. As long as there is no friction, okay, this thing will oscillate forever. Okay, now here's a feature that any oscillating system needs to have. Okay, what is happening is, so let's look at it from an energy perspective. Okay, you can see that, so this is a vertical motion, but if you did an horizontal motion, what you'll have is, okay, now in this thing it has kinetic energy, the energy of motion, gravitational potential energy because it's going up and down, and spring potential energy. Okay, it has three kinds of energies, and the energies oscillating between them. Okay, and you see here are the three sizes of the three energy, but the total energy is constant. Okay, so if you want the system to oscillate forever, the total energy needs to remain constant. Okay, and so for a system to oscillate, what needs to happen is energy needs to go from one form to another and then back and forth. That's what's happening. Okay, so for instance, here's another simple system. Yeah, so you can imagine a valley, and a marble rolls down the valley. Okay, so it has gravitational potential energy, and as it rolls down, that gets converted to kinetic energy. And if there's no loss in friction, then it'll go up as high and then keep going back and forth forever. Okay, so here energy would be oscillating from gravitational potential energy to kinetic energy to gravitational potential energy, back and forth. All right, so for an oscillating system, you need at least two different forms of energies, and the energy is going back and forth from one form to another. Okay? For an oscillating system, you need what is called a restoring force. Okay, here is the equilibrium configuration of the system. If you disturb it from the equilibrium position, the forces that come into play are trying to bring it back there. That's why it's called a restoring force. If you disturb the object from there, the forces that come into play are restoring it back. Okay? And that's what happens in a spring. So let's say this is the equilibrium position of the spring. If you disturb it from the equilibrium position, the force that comes into play are pulling it back there. If you compress the spring, the forces that come into play are trying to bring it back to the equilibrium position. Okay? So this force that acts on that the spring exerts on the mass is called a restoring force. Okay. So for an oscillatory system, you need to have restoring forces. Okay. So when x is positive, this force is bringing it back. When x is negative, the force is positive, trying to bring it back to the equilibrium position. All right. So here's a dynamical system, and we want to describe its system. We want to describe this system. Okay? So we'll learn how to do this. Okay? So here's a very interesting fact. So this looks like a fairly complicated system. And now I'll go back to my horizontal spring. Okay, so let me get a fresh page here. Okay, so to begin with, we'll consider it's a frictionless system. There's no friction between this object and the surface. Okay? And you saw that I take this mass, pull it to the side, and it'll oscillate. And the configuration of the system is changing. Okay? So how do we describe the configuration of the system? How do we describe the state of the system? And you already know this. All we have to do is specify this position, the position of the mass. That one simple coordinate tells you the configuration of the system. So this is a fairly simple system. Okay? And what is it that we're interested in? We have been learning this all along. This is what you want to know. What is the position of this system as a function of time? Okay? What is the configuration of this system as a function of time? That's what you want to know. Okay? Once you know this, you can take the time derivative of that, get the velocity that are involved, take the second time derivative, you get the acceleration and so on. Okay? All right, so now let me work through this. And so the entire chapter is based on these ideas. So I'll sort of summarize the chapter. Okay. All right, we want to know x as a function of time. Okay. All right. So you know the physics of this system. When you pull this mass to the side, what is happening? What is the spring wanting to do? It's wanting to pull it to the left. Okay. The spring force is minus k times x. Okay. And what is force? Force is mass times acceleration. That's what Mr. Newton tells us. And what is acceleration? Acceleration is the second time derivative of the position. So okay, so what we found is the configuration of the system given by xt satisfies this differential equation. Okay? So no matter what you do to the mass, it has to satisfy this differential equation. It has to be a solution to that differential equation. Okay. I'll tell you what we did in a second, but before I do that, let's do a couple more things. Okay. What is k? I'm sorry? Okay. What values can it take? Can it take negative values? No. It can only take positive values. Okay. What is this? That's the mass. Can that take negative values? No. Okay, so this guy is always positive. Okay, so just to emphasize that fact, and to make sure that there's no confusion about it, well, what we'll do is we'll write that as omega squared. Omega is just a constant, okay? We're just writing it like that just because we know that it's the ratio of two positive quantities. Okay, so here is the differential equation. Now, before I solve this, let me go over the stuff again. Okay, so what we had was, we had a system. Yep. Then what did we do? We first decided for the system. So here was your system. We first decided what is the best way to describe the configuration of the system. So you came up with the appropriate coordinate to describe the configuration of the system. And then what we want was, how does it evolve in time? That's what we want to know. Okay? All right, so you came up with a system. Then you put in some physics. Okay? And what did the physics allow you to do? It allowed you to come up with a mathematical model. Okay? What was the mathematical model in our case? Our mathematical model was a mathematical equation describing the behavior of the system. What was that? That was this differential equation. So in general, most mathematical models are differential equations. Okay? Now, if you want to study the system, you can set it up in lab, have very good timers, measuring devices where the location is, and that's a lot of trouble. Instead, well, you're all experts at mathematics, you set up the mathematical equation and just learn to solve this equation. And that's what we're going to do. Okay. Okay. All right, you came up with the mathematical model, then solution. So what do I mean by solution? You come up with that solution. And then what is it that you do? This is what your theory predicted.
Test it to make sure it lines up with reality.
Very good, my friend, very good. So what you do is go check and see, get this to oscillate. See if this behavior is what you predicted. What if it doesn't? Physics is full of crap then. No, if it doesn't, then what you do is you go refine your model. Okay? Add new forces. So if, for instance, if there is friction, add friction, and so on, then come up with the new mathematical model, come up with new solution, till you finally come up with a solution that describes reality properly. So that's what we're about. All right, so for our system, so what we have done is, okay, so this was the system, this was the dynamical system, and we saw that the equation describing the behavior of the system is given by this equation. Okay, so here is the mathematical model. Here is your system, here is the mathematical model. Okay, so this is the differential equation. You'll learn how to solve these equations. Okay, I'll give you the solution. Initially, for simple systems, you just try solutions by trial and error. Okay, so you get good enough where you can pull out solutions from your hat. Okay, and then you learn various tricks to. In a little more complicated situation, you learn various tricks to come up with solutions. Yeah. So I'll write down the solution. Yeah. All right, let's look at the solution. Okay, so here are the solutions. So there is the equation. Okay. Look at this. In the solution, there is omega, which is part of that equation, original equation. A and phi. What are these guys? They're nowhere in that equation. Okay, it turns out these are constants. In mathematics, they say their language they use is they're determined by boundary conditions. In physics, we say that they're determined by initial conditions. Initial conditions meaning how far did you pull and let go. And if you pulled and then pushed this way or pushed that way. So initial conditions would be the initial position and the initial velocity. Okay? So in physics, we say initial conditions t equal to 0. What is position at t equal to 0 and velocity at t equal to 0. Okay, these two parameters will decide A and phi, or A and phi are related to that. Okay, so A and phi tell you the initial configuration of the system. Okay. All right, so now some more terminology of differential equations. Okay. See, this is a second order differential equation. The order tells you the highest order derivative there is. Okay? And if it's a second order differential equation, you have two unknown constants. If it's a third order differential equation, you would have three constants, and so on. Okay? You guys understanding this? This is also a linear differential equation. What a linear differential equation means is, see, this parameter is not squared. This is not squared. Okay? If this was squared, that becomes a totally very hard problem to solve. Okay? So this is a linear differential equation. So one of the things about linear differential equations is if x1t is a solution and x2t is a solution as well, then x1t plus x2t, that is a solution as well. All right? So anyway, all right. So I'll pause now. I've said a lot. Let's make sure we understand this, because this also tells you why you'll be doing differential equations. Okay? All right, so you will be studying some kind of system. So this could be when you're doing, let's say if you want to be a chemical engineer, you are brewing beer or something like that, and a reaction is going on, that's your system. How does that system evolve in time? Okay, you come up with a mathematical model for the evolution of the system. You solve the system. Okay, the mathematical model is generally a differential equation. Yep. So for a lot of systems that you're describing, the model is a differential equation. You learn how to solve it. And if your solution describes reality, then you're home. Okay? And if it doesn't, then you refine your system. Okay? Which is what you do if you're in grad school and stuff like that. You keep refining your system till you get a solution that you're happy with. Okay? And you do all of this without getting your hands dirty. All you do is a few math classes and you're good. Okay? So that's the life of an engineer. And then you go field test it, All right. So here is a differential equation, and this is one of the simplest differential equations. So this is one of the this is one of the more common. When you first learn differential equations, you'll encounter this equation. Okay? And I told you this was the solution. How do I know if this is the right solution?
If you take the second derivative of that and then just plug
Yeah.
it in.
Yeah, plug it in and check and see if it does satisfy that equation. All right, let's do this just for giggles, okay? So I said that xt equal to a cosine omega t plus phi is a solution. Okay. Well, let's do like our friend said, like David here said, take the derivative of that. Derivative of cosine is what? Negative sine. Okay. And then by chain rule, this is, you'll get an omega from there. So minus a omega sine omega t plus phi. And then take a second derivative. And derivative of sine is cosine. And then from the chain rule again, you'll get another omega. So you get minus a omega square cosine omega t plus phi. Okay. So our equation says, d square xt by dt square plus omega square xt should be equal to 0. Okay, that's what our solution should satisfy. Okay, so here's d square x by dt square minus a omega square cosine omega. Okay, so minus a omega square cosine omega t plus phi. Oops. Plus omega square and k. And you see this is negative and there's positive. This plus this is indeed 0. Okay. So that was a correct solution. Right? It turns out that this is also a solution. This is an independent solution. Okay. This is also a solution. All right, and a combination of those two, so you have infinitely many solutions. Okay? So those are the two linearly independent solutions. So x of t a1 cosine omega t plus phi 1 plus a2. Okay, so those are all the possible solutions. Okay. All right. Anyway, that's all just algebra and mechanics. So here's what I want you guys to remember. Okay. So you'll have a system. This is the sort of stuff you'll do going forward. You'll have a system that you're studying. Okay. What you do is you put physics or any. So if you're studying a biological principle, you'd put biology in it, or physics, or whatever science you want to put in there. You come up with a mathematical model, and then you get a solution. This mathematical model generally is a differential equation. You learn how to solve that differential equation. You come with a solution. Check and see if that solution describes your system. If it doesn't, then you refine the system. So it's an iterative process. Eventually, you come up with a solution. Either you get tired or you get a solution that you're happy with. Yeah. And then everybody goes home. Okay? All right, so that's what we're doing in this chapter. You guys understand? Any questions? Any comments, David?
It's going to be interesting.
It is. Physics is always interesting. All right. Okay, so here is your system. It is so this particular kind of oscillation is called a simple harmonic motion. Okay? And we've been actually doing labs. Some of you did lab on this yesterday, and the rest will do today. Okay? So this is simple harmonic motion. And the neat thing about this is, this motion is, okay, so one oscillation is you start at the bottom, go to the top and back. The period of oscillation is independent of the amplitude. Okay? So the time it takes for this oscillation is the same as the time it takes for one oscillation of that amplitude. The period is independent of the amplitude. Okay, that's the neat thing about this oscillation. Okay, and this is called a simple harmonic motion. You have simple harmonic motion when the restoring force is proportional to the displacement. Okay, that's when you get simple harmonic motion. This would be a oscillatory motion as well, but that would be too complicated to solve. Okay, and that would not be simple harmonic. The period would not depend on the amplitude. The period would depend on the amplitude there. Okay, so that's a much harder problem. All right, so this is simple harmonic motion. We'll look at the energy in this motion. We'll look at other simple harmonic oscillators. Okay, so you'll be amazed to see that this equation this differential equation describes this system You take a mass and twist it, and it'll twist back and forth. It describes a simple pendulum and a physical pendulum. You can take any darn mass, and if you pivot it around a point that is not its center of mass, this will oscillate back and forth. And the same differential equation describes all those systems. Very different looking systems, and that same differential equation describes that system. Okay, so that's why you do mathematics. You know, one simple equation is describing all those things. Why would you be interested in something like this? So here's a physical pendulum. Okay, this is a physical pendulum. You can take this. Okay. This oscillating like that. Why would you be interested in that? Because you can calculate the period, and when you're walking, you're like a pendulum. You're like an inverted pendulum. You can calculate the period of oscillation for that, and that's half a period. You can calculate your walking gait, and it works out. You can calculate the walking speed of all animals, like that. All right. So here's the system that we're studying. Okay, there's the equilibrium configuration of the system. So this is a dynamical system, like I said. You pull this mass aside and it'll oscillate. And as it's evolving in time, what we want to understand is how does this system evolve in time? That is, if you pull that aside, how does this change? What is x as a function of time? Okay, so one of the first thing, well, you know, you're physics experts, so you already know that when you pull this to the side, the spring pulls it back with a force proportional to the displacement. There is Hooke's law. Okay. Well, the force is mass times acceleration of the object, Mr. Newton told us, and acceleration is d square x by dt squared. Okay, so here is the mathematical model describing the behavior of this system. Yep. And then we went through all the algebra. So we wrote k over m as omega square. Again, why did we write k over m as omega square? I forget. I'm sorry? It's always positive. That's what we want to convey. Okay? Omega squared is positive. And so here is the differential equation describing the behavior of the system. Okay? And so now it's just a matter of finding a solution to that differential equation. Okay? And here's the solution. Okay, so in this solution there was this constant A and phi that were not part of the original equation. Only omega was a part of the original equation. Okay? And what will determine these constants, A and phi? Boundary conditions. That's what the mathematicians call it. And physicists like to, we say it, initial conditions. Okay. So what was the position of the system at time t equal to 0, and what was its velocity? Okay, you saw that if this is a second order differential equation, and that's why you had two constants that are determined by initial conditions. What if it was a fourth order differential equation? I'm sorry? Yep. So you need four conditions, okay? And so on. All right. So once you have the solution, what are you interested in? You're generally interested in the velocity of the object, okay, and the acceleration of the object. And you just take time derivatives of those and you get that. Okay, so once you have this, everything else you want to know about the system, you can easily determine. Okay, and so that's the recipe. All right, again, system, model, solution. Okay. A is called the amplitude of the motion. That is the maximum distance it goes from its equilibrium position. Okay, so okay, so if you pull the mass aside that distance, this is called the amplitude. Yeah. And once you let go, if there's no friction, it'll come back minus A here and then oscillate back and forth like that forever, okay, if there's no friction. A is the amplitude, and this is called the phase. This entire thing is called the phase. So that's the initial phase. Phi is the initial phase. Okay? Omega is the angular frequency. All right. So this is the solution is either a cosine or a sine function. And this just physically illustrates that that solution is correct. Okay, so what this is showing you is, okay, so what you do is you roll this paper at a constant speed. That simulates time. Okay, so that simulates time. As time increases, x should change as cosine function, like that. Okay, as time increases, x is changing like that. That's what this function is telling you, is the cosine function. And then you can see that you attach a pen to this mass, and as it goes back and forth, you get a sine or cosine curve. So this is a physical illustration of this solution. All right, the period is the time it takes for one oscillation. Okay, so that's one complete oscillation. It starts from here, goes there and back. Okay, if you started from here, you would go there, that would be one complete oscillation. Okay. If you started from here, you'd go there, that is one complete oscillation. Okay. All right, the time taken for one complete oscillation is the period. Okay. And it turns out that the period is 2 pi times the mass divided by the spring constant. Okay. So let's see if it makes sense. Okay, that's the mass attached. So this is the given spring. Let's say if you have the same spring, but you make this mass heavier, you attach a heavier mass, you would think that it's plausible that now the time it takes to go back and forth to complete one oscillation would be greater. Okay, so that's what this equation is saying. If you increase the mass, the period will increase. For the same given mass, if you attach a stiffer spring, one oscillation will be completed faster. Okay, so a stiffer spring gives you a smaller period. Okay? So that's what the equation is telling. Yeah. Frequency is how many oscillations you do per second. And frequency is 1 over the period. Okay? So that's 1 over 2 pi k over m. David? Go ahead.
Divided by 2 pi. That was something like h bar had something to do with that, right?
Yep. So h bar is h over 2 pi.
Yeah.
Very good. Yep.
So is h a period and then h bar is a frequency?
No. We just define that because in all the formulas in a lot of formulas that you come up with, it comes in this combination.
That makes sense.
Yep.
Still cool.
Yeah, it is cool. So if you have to write something 100 zillion times, you come up with a new symbol for it. Okay, because inherently, well, anyway. All right. So in this business, when you do all of that stuff, you come with C so many times, H bar so many times when you're doing quantum field theory and all. Okay. So the next laziness step is we'll just call them 1. And so they don't even put that there. Okay. And then at the end, when you get a result, you know what should go where, just from dimensional analysis. Okay. So that's how they do that. All right. So frequency is 1 over period, and it's that. All right. So that's the simple harmonic oscillator. Okay. Again, here's the system, a mass attached to a spring. Here's the equilibrium position. Okay. You pull this guy to the side and let go, and he'll oscillate. Okay. X as a function of time gives the configuration of the system and tells you how the system is evolving. Okay. And this configuration satisfies this differential equation. That is, the behavior of this system is given by this differential equation. Okay. All right, so that's everything that we've talked about so far. Okay. The solution to this differential equation is that. And once we have this, you can calculate everything else that you want to know about the system. So once you have this, you can calculate the velocity of this mass at any time. You can calculate the acceleration of this guy at any time, and so on. Okay, and that's all we generally want to know. The maximum velocity is given by, okay, this is a constant, that's a constant. The only thing that is changing is this. And the maximum value this guy can take is 1. So that's what the maximum velocity is. So this is the magnitude of the maximum velocity. It's negative when it's going to the left, and it's positive when it's going to the right. And maximum velocity, the maximum speed, occurs when it's in the equilibrium position. It's going the fastest when it's here, either in this direction or that direction. When is it going the slowest? I'm sorry? Very good. At that distance, it's come to rest. Okay? So at this point, the velocities are 0, at the extreme points. When is the acceleration maximum?
What would be the equilibrium position for the stationary?
Okay, so here, let me show you a trick. There's this equation telling you the force on the object. Acceleration is maximum when the force is maximum. force is maximum when x is maximum. So when it's at its extreme position, that's when the acceleration is maximum. Okay? Yeah. So yeah, acceleration is 0 here. Acceleration is maximum at the extreme points. Velocity is maximum here, and velocity is 0 here. So they're opposites of each other. Okay? Did you guys understand that? All right. Now I'm going to fly through a few slides, okay? Because what we want to do is, so here was our model. Oops, what happened? Where did it go? Okay. Okay, so we had our system. We put in a little physics in it. We sprinkled a little physics in it. We came up with a mathematical model. We came up with a solution. Then we'll see the solution we've come up with is not good enough. So we'll learn to refine it. Okay? The solution we came up with will not be good when what is present? Friction is present. Okay? So in the next step, next iteration, we'll learn to put in friction. Okay? So, but that'll come in about 10 slides. So what I'm going to do is fly through the 10 slides and then give you a little break, and then we'll come back to that. Okay? All right. So now we'll study torsional pendulum. Oh, well, okay. So energy of a simple harmonic oscillator. Okay, so this oscillator is going back and forth. You saw that a spring has, when the spring is stretched, it has potential energy stored in it. When it's compressed, it has potential energy stored in it. Anybody remember how much potential energy there is in a spring? Anybody remember the formula? Very good, my friend. What would I do without you, David? 1/2 kx squared is the potential energy. Okay. What is the kinetic energy in the system? Kinetic energy is 1/2 mv squared. Okay. So m is the mass attached to the spring, and v is the velocity of the spring. Okay. X, okay. X is a function of time. And v is a function of time. Okay. So there is x as a function of time, and there is v as a function of time. Okay. So the total energy is kinetic energy plus potential energy. Here is the kinetic energy, 1/2 mv squared, and now put in the expression for v, and there is kinetic energy as a function of time. See, it's a function of time. There's potential energy, 1/2 kx squared, and that's a function of time. And that makes sense, as this thing is oscillating back and forth. Its kinetic energy is changing, its potential energy is changing. Okay. Now let's add the two. And you see, it's constant, it's not changing with time. The sum of the two is not changing with time. Okay, so that's another thing that you're always looking in systems. Okay, so here is a system that's changing in time, that's the motion looks complicated and stuff like that. You always ask a question, is there something that is constant? Okay, so that's one of the features that you look in dynamical systems. Yeah. And here it turns out that this guy, sum of kinetic plus potential energy, this is called mechanical energy, that is constant. Okay, and that's equal to 1/2 times k times the amplitude square. Okay, that's the total energy. All right, what this formula gives you is, okay, so this gives you the speed of the object as a function of position. Okay, when it's at the extreme point, what is its speed? 0. When x equal to a, velocity would be 0. When is it going the fastest? X equal to 0. When x equal to 0, the equilibrium position, that's when it's going the fastest. And this formula is giving you that. Okay, the plus sign telling you that when it's going, the velocity is positive when it's going in that direction. The negative sign telling you the velocity is negative when it's going in this direction. Okay? So this is giving you the velocity of the object as a function of position. Okay. All right, now I'm going to speed up a little. Okay, so what did we study? We studied simple harmonic motion. When is a motion simple harmonic? It's called simple, by the way, it's called simple harmonic if the period is independent of time and the position is given by the configuration is given by a sine or a cosine function. You get simple harmonic motion when the restoring force is proportional to the displacement. Okay? The greater the displacement from the equilibrium position, the larger the restoring force. Okay? All right. So here are some other examples of simple harmonic oscillators. Okay? These are all simple harmonic oscillators. This restoring force or torque or whatever it is are always proportional to the displacement. Okay? Okay, so you take a disc and attach a metal wire, and if you twist it, it'll oscillate back and forth like this. Okay? This looks like a very different motion than the mass attached to the spring, but the motion is very similar. Okay, and the configuration, so I'm going to erase that. The configuration is given by theta. So this is the equilibrium position, theta, and this is what we want to know. What is the theta as a function of time? Okay, how does the configuration of the system change? Okay, so you could have any object, take a stiff metal wire, attach it to the center of mass, and you twist it, and it'll oscillate back and forth. Okay. Of course, if you take a cooked piece of noodle, it won't twist back and forth. You take copper wire, it'll twist back and forth. What if I take a titanium wire? Will it twist back and forth faster than copper? Yes. Okay. A stiffer wire, okay, will make it twist back and forth faster. It's like a stiffer spring. Okay. So it depends on something called the torsion constant, and this guy is a torsion constant. He is kappa. The torque is proportional to the displacement from the equilibrium position. Okay. See, the restoring force or torque is proportional to the displacement. So what you'll get is a simple harmonic motion. Okay. In this case, the solution will be either a cosine or a sine function. Okay. All right. What does Mr. Newton tell you? You apply a torque on an object that will equal to I times alpha, the angular acceleration. Alpha is d squared by theta by dt squared. Okay, so this is Newton's second law, and we plug that in here. So I d squared theta by dt squared equal to minus kappa theta. Okay, so this is exactly the same equation as for the case of the mass attached to a spring. Okay, you will divide by I, and again kappa is positive, I is positive. I is the moment of inertia of this guy about that axis. Okay, that's what I is. So we call it omega squared. There's the solution. There's the equation. The only difference is in the previous case we called the configuration of the system was given by xt. In this case, the configuration of the system is given by theta t. but they both satisfy the same differential equation. Okay, it's just a different coordinate is giving you the configuration of the system. Okay, you guys understand? Okay. Omega is kappa, square root of kappa by I, and the period, the time for one oscillation is given by 2 pi I over kappa. Heavier this disk, greater the period. Okay? Stiffer the material, bigger kappa is, smaller the period. So if you had a copper wire of the same dimension and a titanium wire, the titanium wire has a greater K, kappa, and that thing will oscillate faster. Okay? Here's what is called a simple pendulum. A simple pendulum is a heavy mass attached by a light string. A small heavy mass attached by a light spring is called a simple pendulum. Okay? So if you disturb it there like that, there's the weight of the mass and there's the tension. Okay. This component of the weight is balancing the tension. Okay, right now the tension is smaller than the weight. Okay, so this component of the weight is balancing the tension, and this component of the weight is restoring the system to the equilibrium position. Okay? And so if you take a pendulum, disturb it like that, it'll oscillate forever, like that, back and forth. How long will it oscillate like that? Forever, if there's no friction. Okay? All right. So this component of the force is mg sine theta. Okay? And mass times acceleration of this guy is mass times d squared s by dt squared. S is the arc length. Okay? And the arc length is given by the radius of the circle, which is L in this case, L times theta. Okay, so this arc length S is given by that, and so S is L theta, and so second derivative of that. Anyway, you can write all of that. You can go through the algebra. D squared theta, this theta as a function of time. That gives you the configuration of the simple pendulum. D squared theta by dt squared is equal to that. And if the angles are small, okay, so you can test this in your calculators, put it in radian modes. As long as theta in radians is less than 0.1 radian, then sine theta is approximately theta. Okay, so put your calculator in radian modes, do sine 0.05 radian, and you'll get 0.05. Okay, so 0.1 radian is about, how much is 0.1 radian? What is 1 radian? About 60 degrees. So 0.1 radian is about 6 degrees. Okay, so as long as you're not going past 6 degrees, okay, so this is equal to that, and you get this equation. You get the same differential equation. Okay, so it behaves simple harmonically. If you take a pendulum and you set it, if you start it oscillating from 45 degrees, then the period won't be independent of the amplitude. Okay, okay, so there's the period again, 2 pi over length divided by g. Okay, so, okay, and this is the basis for pendulum clocks. Okay, so you can take a pendulum whose length is such that the period is 2 seconds, So every time it goes there, that's 1 second, 1 second, 1 second, 1 second. Okay? And again, the neat thing about this is independent of the amplitude. Okay? So, like I said, this was the basis for one of the more accurate clocks. And I told you the story. Mr. Galileo was at church, an earthquake happened, and the chandelier started oscillating. And he timed it with his pulse. And he saw that, so this was the genius of Mr. Galileo. He noticed that as the oscillations died down, the time didn't change. Okay? There was a room full of people noticing that oscillation, but Galileo figured out what that meant. Okay? So he discovered the first simple harmonic oscillator, and that's why grandfather clocks are good. You know, you can set it in oscillation, and as the day goes by, there's always friction in real systems. But as the oscillations die out, it's still keeping good time. Okay. All right, so here's a physical pendulum. You can take any darn object and pivot it about a point which is not through the center of mass. So you pivot it about that point, you disturb it, and it'll oscillate back and forth. The restoring torque is mg, that's the weight, times the moment arm. So the torque is this force, and you're calculating the torque about this point is there's the moment arm. mg d sine theta, that's the moment arm. Okay? That's the restoring torque. And so the configuration of this system is given by that. So what you're interested in, how does theta evolve? And so I times d square theta t by dt square go to mg d sine theta. Okay. And we just told you a second ago that if theta is less than 0.1 radians, then this will be equal to theta. Okay, so for small angles, this is sine theta is equal to theta. Okay, and then you get back your differential equation that you become so friendly with. Okay. So there is your differential equation, and again we'll call this, since this is positive, we'll call it omega squared. So the same differential equation is describing this system as well. So what was happening? Just the meaning of this omega square was changing for all those different systems. Okay, so for the mass attached to the spring, this was K over M. For the simple pendulum, this was L over G. For the torsional pendulum, this was I over kappa. Okay, so omega square was different for different systems. So this was K over M for your mass attached to the spring. It was I over kappa for the torsional pendulum, L over G for the simple pendulum, and for the physical pendulum, it's mgd over I. Okay, that's it. All right, so the period for this was I over mgd. Okay, and again, this is not of just academic interest. You can calculate, like I said, you can calculate the gait of an animal. Your leg is sort of a physical pendulum, okay? And you can calculate the walking speed of an animal doing that, okay? All right, so you saw that a mass attached to a spring, you disturb it from its equilibrium position and it'll oscillate back and forth like that. Here's an interesting fact. Okay, if something is going in a circle at constant speed, uniform circular motion, it turns out that this is related to this motion. you would never guess that. Okay? At first blush, nobody would guess that. But it turns out that this, if you're going around in a circle at constant speed, this is related to that. Okay, so that's what this illustrates. So here's a ball. This thing is rotating. This has a constant angular speed, meaning this is going around in a circle at constant speed. And if you shine a light like this and project the shadow of this guy, there's the shadow, and the shadow will go back and forth. And the motion of the shadow is exactly the motion of that mass. Now you could do that another thing. So here is this circular motion. You can shine a light like this and get another shadow projection here. This is also a simple harmonic motion. So uniform circular motion is a sum of two simple harmonic motions. Okay. In fact, we told you about this a little while ago. Do you guys remember if this was Earth and you dug a tunnel through the Earth? Remember, if you stepped into the tunnel, you would execute a simple harmonic motion. And what was the period of that motion? That was for half the time, 85 minutes, about 90 minutes, and that's the time for the International Space Station. Okay? That's a uniform circular motion. Okay? So that motion is related to this simple harmonic motion. So there's lots of neat things hiding underneath. Okay? All right, so these next two slides show that to you, and I'm not going to go to the details. Okay, so here's uniform circular motion, an object going in a circle at constant speed, and when it's at this angle theta is equal to this angle theta. Okay, the x component of this velocity is that. All right, and if this angle is omega t plus phi, what does this mean? Phi is the angle at time t equal to 0, omega is the angular speed, and as time is increasing, this angle is increasing. Okay, so this guy is going around the circle. Okay, so that's what that is telling you. This angle is equal to that angle, and this angle is 90 minus this angle. Okay, so this velocity is v times cosine of this angle. So anyway, it all works out to this. And what this is telling you, v is the magnitude of the speed that's related to the angular velocity and the radius of the circle. The radius of the circle is equal to the amplitude of oscillation. Okay, so this component of the velocity is that. Okay, so for a uniform circular motion, that's equal to that. And that's exactly there. A omega sine omega t plus phi. Okay, so that's the velocity of the mass attached to the spring. Okay. Here's the acceleration. And okay, so when you have uniform circular motion, you have centripetal acceleration, and the centripetal acceleration is given by v squared by r. Okay, r in this case is the amplitude. V is given by amplitude omega, so a omega squared. So the magnitude of this acceleration is a omega squared. Okay, and if you calculate this acceleration, this component of the acceleration, it's equal to that, a omega squared times cosine. That's what it works out to. And that's exactly the acceleration of the mass attached to the spring. Okay. So we're showing you that the projection of velocity and acceleration along this axis are the same as that for a simple harmonic oscillator. Okay. All right, so again, the point of those slides were uniform circular motion is a combination of two simple harmonic motions. Okay. All right, so we studied simple harmonic motion without friction. That's what we did in this 1 hour of change. Now, we are tired, but after a 5-minute break, we'll be refreshed. And then what will we do? We'll add friction. And that's the next step, okay? And that's what we'll take. All right.